Well, thank you, Rob, and thank all of you for being here today, this evening. I'm going to talk a little bit about some of the experience we've had with the Aspect system, and I've narrowed my talk into a couple of different topics. I want to talk a little bit about the installation because some of you may be interested in how hard is it to do. It's actually not hard at all. In fact, it was loads of fun. We'll show just a little bit of the animal setup because that's an important part if you're trying to do the throughput that many of our users need. And then I'll show you two longitudinal studies that we've undertaken in collaboration with people at Charles River. A few slides on 1T versus 7T, and then finally close with a little bit of work that one of my graduate students has done recently. So let's start with the installation. I tried to count the number of MR installations with which I've been involved over the years, and I ran out of fingers, so I couldn't do it. So it's been something that has always sort of had me concerned. And then I got the chance to do this. This is the Aspect system coming in. That's all I had to do. I had to rent a front loader. And I drive by Sunbelt on the way to work every day. And so I stopped one morning. I said, can you guys drop a front loader off tomorrow? They said, sure, you know how to use it. I said, oh, hey, yeah, sure. I mean, hell yes, I know how to run a front loader. It was great. I mean, I got to, Michael was sitting there just a little bit concerned about whether I was going to drop the thing. But it worked fine. I was able to run the front loader. It cost me, so my total installation bill was $120 for renting this. And I would have paid the $120 just to get a chance to run the front loader. So that was cool. And there it is coming, being sort of lowered gently. This was the point where Michael turned a little green. He wasn't quite sure that I knew what I was doing because the first time I hit the litter, it sort of jerked down a little bit, but we got it mounted there quite easily. He's doing the real work, and we just rolled it down the hall, put it in the room. There's plugs right there and there. I had no electrical modifications. I didn't have to modify any chilled water. I didn't have to do anything with air conditioning. I didn't have to do anything except rent the front loader. And any of you want to do that, I really enjoy running the front loader. So just give me a call, I'll come. Yeah. And in one day, we went from everything in the box to the thing actually working. I was just incredulous. It was pretty astounding. So there's the rack. That's it. That's the whole thing there. That and that. Then the computer sits over here. This is our own stuff for the animal setup and physiologic monitoring and such. I have 4 7 Tesla systems. 3 of them. I'm putting a 4th one in now. Into the room right next to where the Aspect has gone in. One of the systems that went in about 3 years ago, it went over the area that where you drive into the building. The modifications of the room, because we had to shield the magnet had to be shielded, and then it weighed enough that we had to reinforce the floor. The modifications for the room cost $850,000. The modifications here that I'm having to pay right now for the installation of my 7 Tesla system are going to be on the order of $100,000. There's several different transformers, up and down, extra power. Right there, chilled water coming in. Chilled water has been a nightmare getting it in and out of the building because at one point they were going to run chilled water from the next building because we weren't meeting the specs. So it has been a delight to just be able to roll the thing in and plug it in. I'm delighted to have this new system that we're putting in, but it's pardon?
What about the shielding?
What shielding?
Is any shielding required?
There is no shielding required for the Aspect system at all. None, 0. I mean, just you pull the animal out, put him in, put it in. There's no RF shielding. And we haven't had any problems at all with RF lines, birdies showing up in the scanner. I think we had one problem one day that was traced back to a loose connection on one of the gradients, but basically the shielding has not, it's been a non-issue. When we installed our first MR system back in '83 in the clinical arena, just the shielding for us on those $250,000. So no, I mean it is simple. So animal setup, I just thought I'd include this so you can see some of the ease of use of it. This is our setup, but now the Aspect people have put together a streamlined system. This is the assay instruments panel. The assay instruments comes with it. We use the assay instruments on all of our systems, and it gives you cardiac and respiratory information. And then the applications. We've had the good fortune to work with folks out at Charles River for quite some time now. Charles River has about 40 different human xenograft tumors, and they're right in the research triangle. It's absolutely fabulous arrangement for us. We can literally call up on Tuesday and say we would like a colorectal cancer next Wednesday, and a week later, animals show up. We work through all the DLAR and animal transport things so that we can get them in and house them in our own building. So this is a study where there was a subcutaneous injection in the flank tumor, female nude mice, 8 to 12 weeks, and the tumors were selected after inoculation to be about 1 millimeter cubed. We used the Aspect system to image at 13, 15, 19, 21, 23 days. We use gadolinium liposomes. These are the nanoparticles that are a blood pool agent. They are decorated with polyethylene glycol. And I think you'll see that a lot of the studies these days are going to use some sort of biologic, some sort of contrast agent. This is the agent. It was actually developed by one of our colleagues and collaborators, Srini Mukundan, in which the agent is the liposome with a lipid layer, and there's aqueous gadolinium DTPA, either Magnavist or Prohance. There are several different variations of this. And then polyethylene glycol on the surface. And now they're decorating the surface with a chelated gadolinium compound as well, so the relaxivity is even higher. It's about 100 nanometers, so it stays in the blood pool through the course of the study. And in fact, there's some very interesting things. We've done some of this, used some of these with for in CT studies. It'll stay there for 72 hours or so. So you can monitor extravasation in a tumor over a much longer period. That was not the focus of this particular study, but it is something that we're anxious to follow up on with the Aspect system. So this is just a QuickTime movie going through, and the images will get considerably better. I wanted to start with our first ones and show you where we started and where we've come. That's the individual slices. You can see individual slices of the tumor. But here's what we were most trying to do. We were actually trying to look at the vascular. The colorectal tumor is a highly vascular tumor. So we wanted to follow the development of the vascular structures in this. So this is a maximum intensity projection through the 1 millimeter slices. There are about 16 1 millimeter slices through this. About 8 of them cover the tumor at this stage. And here is an example showing at 2-day intervals, 4-day intervals, 2 days and then another 4 days, then following again. And along the way, we see the development of the vasculature. This was kind of an interesting phenomenon that we were unaware of, but it makes sense. This is an SSFP being set up in here, probably with pooling of the agent. Do you buy that? I have to be careful with Dr. Linkinski here. He's probably going to make me honest, and I won't be able to blow too much smoke. So you think that's SSFP? Thank you. I'll pay you afterwards. We'll meet out behind there. So we took it a little bit further, looking at a surface coil, and this was a surface coil we built in-house. And so here is using the body coil, and this is only about a 15-minute scan. It's a 3D gradient recalled echo. I think it's about a 128 cubed, 15-minute scan, and you can see a great deal of vascular detail. So we're going to go back and revisit this now with some surface coil studies. The next thing that we were looking at was a human glioma model. Our friends at Charles River have been particularly interested in this. They have a number of their customers, and we work with them and their customers on their models. One of the big problems with these intracranial injections is, did you hit the right spot? And so you can end up doing survival studies on these animals as your endpoint. You can't see inside. You can't use a caliper. So the only thing you have to do is sort of look at behavioral things. And when the animal starts weaving around the cage, sort of like me weaving around the lab, you say, well, maybe there's something wrong with the animal. But clearly, being able to image in vivo, and particularly looking at culling the animals beforehand. So again, a female mice, 8 to 12 weeks old, using an injection which was stereotactically guided, about 10 to the 6 cells. And we looked post-implant at 1, 3, 5, 15, and 20 days. We had about 10 animals, and because of the ease of use, we were able to image all 10 animals 5 times. So that's been a first for us, the challenge of just keeping the animals alive. If you're handling them a lot, that adds to your morbidity, and the setup is simple enough that you just put them in the nose cone, there's no intubation, and everything just seemed to work well. We also did some studies on one of our 7 Tesla systems. This is a system with a GE console on it, and this is a high-end RF coil. This is it actually costs the same as my Tacoma pickup truck, so that's equivalent to 1 Tacoma pickup. It's amazing what you could buy if you didn't spend your money on MRI stuff. I could have a whole fleet of pickup trucks. Anyway, here's the setup in the aspect system. And these are T2 weighted images, a multi-slice sequence that takes about 40 minutes, 1 millimeter slices. Tumor is outlined exceedingly well. We're going just through those 1 millimeter slices. This is an axial scan, a different scan. These are anisotropic scans. I think the resolution in plane is about 120 microns. 1 millimeter slices. Again, you can outline the tumor quite nicely. Here we scanned a bunch of the animals at 7 Tesla as well. Here is the same series of slices going through the 7 Tesla. They are better. The signal to noise is better. But we'll see in a minute, you draw your attention to the tumor here, you're seeing some sort of heterogeneity, but if you're looking for the size of the tumor, this is, to me, sort of a killer slide because we've got 4 different time points. This one we had to scan a day later on the 7 Tesla because we were having trouble with it a couple days later. But these are, Nick did a wonderful job of matching this animal up at the same slices. Day 11, day 11. And so now, the longer T2 at lower field shows up with contrast. It's a little bit better. I did not measure the contrast to noise. I don't want to get into those sort of arguments right now. But I would say that our ability to outline the volume of the tumor is at least as good on the 1T as it is at the 7T. They were both scanned using a standard spin echo sequence, and we tried to adjust the spin echo sequence to be as close to apples and apples as possible. This one had a slightly smaller diameter coil. It was 20 millimeter solenoid versus a 32 millimeter birdcage coil. This was a quadrature birdcage coil. So it's not a bad comparison. This was a particularly relevant part of the study for our friends at Charles River. This was a normal glioma injection. By normal, I mean that they hit the spot that they wanted. They wanted to get into one hemisphere. They didn't want it penetrating the other hemisphere. You could see at 1 day a little bit of edema where they have implanted the cells. And at day 19, you can see the tumor pretty much isolated on the left half of the brain. Here is an injection that didn't work, and that's a very useful thing for them to know as well. When they take these animals out, they want to take these animals out of the cohort. We kept this one in so that we could see at 1 day they actually hit the ventricles, and so at day 19 you see spread of the tumor on both sides of the brain. Since we had that one, we wanted to play a little bit. So this is a lower resolution. It's a 128 squared. This is 256 squared. But we were able to use the inversion recovery scheme, and you can see that we can differentiate some of the structure in the tumor a little bit better with that inversion recovery. I think there's a fair amount for us to do yet in rediscovering some of the pulse sequences that we maybe discarded some years ago. So I'd like to close today with a little bit of discussion for another longer range project we have underway with the Aspect machine. This is work that Gabriel Howells, one of my graduate students, has done. Gabe did his MD and his PhD with us at Duke and is now at Stanford. And his project was to look at the blood-brain barrier, many of you, and ways that we might alter the blood-brain barrier. So the blood-brain barrier, as you probably know is specialized endothelial cells creating very tight junctions. And these junctions restrict the material into the brain. So if you would like to do therapeutics, get them into the brain, you are faced immediately with the problem of opening that blood-brain barrier. If you're trying to do, as Gabe was, fMRI studies, you've got to be able to get the calcium, the manganese into the, across the blood-brain barrier to do those functional memory studies. So the way he developed this was, this is a column of water shown schematically being placed down on top of the mouse, and we put a single transducer in there that works at 5 megahertz, and there's a protocol where we pulse that transducer with calibrated amounts of power that are sufficient to shake, to sort of cavitate an ultrasound contrast agent, but we do not heat the tissue. So this is far below the level of energy that would be necessary to do heating. And as a consequence, we can non-destructively open the blood-brain barrier. We can open it, it stays open for about 30 minutes, during which time we can pass whatever we choose across the blood-brain barrier. If we're doing a therapeutic, we can mark that therapeutic with a contrast agent and actually titrate the amount of contrast flowing across that barrier. The key is one of these ultrasound agents. This is a perflutin gas. It's actually a fluorine gas inside a protein bubble. So the bubbles you can see here are just a couple of microns. They are injected with the contrast agent prior to the initiation of the ultrasound. And the interaction of the ultrasound with these perflutin bubbles pushes, sort of massages the blood-brain barrier to open it up. This shows the setup physically. We're actually using components from a Visual Sonics ultrasound system here to do the positioning. So this is dark. This is a control. This is about a 30-second scan at 7 Tesla of a C57 black mouse, just with a standard spin echo. This is after injecting Magnavist. You can see the muscles light up a little bit, but the brain is still quite dark. This is injection of the Magnavist and the contrast agent that is used for ultrasound, the Definity perflutin bubbles. Again, the contrast agents in combination do not open the blood-brain barrier. But when we apply the ultrasound for about, I think it's about 3 minutes worth of scans, you can see that the blood-brain barrier opens up marvelously and there's significant enhancement. All 4 of these images have been displayed with the same grayscale, so this is a realistic definition of how much enhancement you get. You get enhancement of 5 times, 3 to 5 times the signal for a standard T1 weighted sequence. And so this in vivo staining lets us look at altering both the definition of the anatomy and also looking at introducing things that will allow us to do functional studies. This is a comparison of the animals done at 1 Tesla and at 7 Tesla. And not surprisingly, it's surprising to us initially, but in this case, we were actually pleased with the 1 Tesla images over the 7 Tesla because you can see here there's very little of the artifact. This is susceptibility artifact. Susceptibility artifact comes up and grabs you at higher and higher field. Now, to be fair, perhaps if we do some titration here with the 7 Tesla images, we can get to a point where we're not fighting this, the susceptibility artifact. But at this point, we are delighted with the results that we're getting here. It ain't broke, so we're not going to go ahead and fix it. So the conclusions that I have for you today are that preclinical imaging with the 1 Tesla has provided very real answers to real questions that some of our users have had burning on their burner right now. Can we do this? Can we do it easily? And the young man that has been doing all the work, it's one person does it. He does all the setup. He does all the running. He's done up to 10 animals in a day. He just sort of walks in there, cranks it up, and starts to study. The cost of installation has been trivial. I didn't add the extra feature that you get to drive a forklift, if that rings your bell. And the aspect people have done a nice job in attending to the biological problems and the setup so that you can actually bang through a lot of animals quickly. System is exceptionally easy to use. We don't have all the bells and whistles that we'd like in an academic institution, but for the use that we have targeted, it works extremely well. There is a very easy interface, and you can bang through the images quickly. And from our perspective, it represents a major advance in making MR imaging accessible. I keep telling our friends at Aspect that I'm going to turn them all into Lutherans because it removes all the priests guys like me who say, well, you know, you guys can't really manipulate the MR. You got to have somebody that has a Ph.D. in physics who tell you what the magic is. The magic is removed, and I think it's a much more accessible system, and I expect to see its penetration into the market quite dramatically over the next couple of years. And with that, my grandson and I both say thank you very much.